Greetings folks, it's Professor Fiore. Today we are going to talk about the high frequency performance of a simple BJT amplifier. Now before we get into this, I'm going to suggest that you watch two videos, if you haven't already done so. The first being on Miller's theorem, the second being on the low frequency performance of a BJT amplifier. Once we have that behind us, we'll have some analytical tools and perspective that will make looking at the high frequency response a little bit easier. So let's go and look at our circuit. Here we have a single stage common emitter swamped amplifier utilizing a split emitter bias. Let's do a quick set of calculations on here. So for the DC, we could make the approximation that the base is about 0 volts DC. We'll lose 7/10 across the base emitter. And that'll leave us with around minus 0.7, maybe minus 0.8 at the emitter, and about 9.3 volts left from the 10 volt power supply to drop on this total of 47K. So that'll give us a little bit less than 0.2 of a milliamp. If we pass that 0.2 through this RC value of 50K, we're looking at about a 10 volt drop. And when we subtract that from this VCC supply of 15, we'll be looking at about 5 volts at this collector. And that will end up achieving about 6 volts from collector to emitter. All right, we're going to need that a little later, so remember that. We need about 6 volts from collector to emitter. We can also figure out the gain. Given the current of about 0.2 mils, we would divide that into the 26 millivolt constant for R prime E. So 26 millivolts divided by the 0.2 mils gives us about 130 ohms. So our gain would be the AC value of RC, or 50K in parallel with 100K for 33 1/3 K, divided by the swapping resistor of 1K plus the R prime E of 130. And we'll be looking at a gain of about 29 or so. All right, so I've got a 1 millivolt input. We're going to multiply that up by 29. Take a look at the output. I'm using a fairly small input here because I want to make sure that we don't get any distortion. I want to look at that waveform and make sure it's a nice pristine sort of waveform. Okay? All right, now let's just do a quick DC analysis over here just to sort of cross-check, sort of a sanity check, right? Make sure everything we did is okay. So let's take a look at the collector here, node 7, 5.4 volts. Looking good. We expected a little less than 5. And the emitter is just about 0.8. So again, we're going to have about 6 volts across that collector emitter. So far, so good. Take a look at the collector resistor, and we can see we're getting 190, about 192 microamps, so a little less than the 0.2 mils that we expected. That looks good. And right above it is the base current, which is a little over 2.5 microamps. That'll give us a beta of about 75, which is a little low compared to some of the other things we've done, but this is biased at a lower current. And remember, your beta is a function of that bias current. So this is not too surprising, right? All right, so the DC looks pretty good. Let's go over and take a look at the AC part using a transient analysis. And I look at the V in here, which is the green. Nice sine wave, pretty small amplitude. It's only 1 millivolt. More importantly, we look at V load, the maroon trace. That is a minus sine wave, so we're getting the inversion. It looks pretty good just by eye, but we can check some symmetry here with a cursor. And where do we peak out here? So we're getting about 28.5 on the positive and about that same thing on the negative. All right, so we're getting a gain of about 28.5. Again, we're going to need that in a bit. And that's inverting. So looking good so far. All right, I'm going to do a quick AC frequency analysis here because when we looked at the low frequency performance, right, we were concerned with what was going on down here. And right now, I don't care about that. I just want to look at the high end. And we're seeing a similar kind of thing, sort of a mirror image, right? The high end is rolling off over here. Our goal here is to figure out where this frequency is. How do we calculate that, where this thing starts to roll off? What causes it? What are the components? When we looked at the low frequency response, it was the input and output coupling caps and bypass cap that controlled that. And by controlling their values, we control where the low frequency cutoff is, right? We get 3 lead networks essentially. And the highest of those 3 is the dominant one. It's the one that affects the midband response first. And there could be some interaction between them if they're close to each other. All right, I don't see any little capacitors out here that are affecting the high frequency response. Well, you won't, usually. These are small parasitic capacitances associated with the active device. So if I look at, for example, the base 2 collector on my transistor here, you could think of that reverse bias junction, right, the depletion region, you could think of that as kind of like the dielectric of a capacitor. And the base and the collector themselves is like the plates of a capacitor. So that'll produce a small capacitance here. Similar sort of situation on the other sets of terminals. Well, how small? Well, probably picofarads. And at lower frequencies, at audio frequencies, the capacitive reactances that are produced are big enough that we can ignore them, You push the frequencies higher and higher. Don't forget our handy-dandy frequency equation over here. As we go higher and higher and higher, that is no longer true. We can't ignore them. They start impacting the performance. Okay? All right, so how do I find these little capacitances? Oh, and by the way, before I go any further, that's just for the transistor. In reality, there are small capacitances associated with all the resistors plus wiring. You might have an input capacitance for the following stage. Maybe you have some coax cable out here. That could have 20, 30 picofarads per foot. So these things can add up. But let's focus in on this transistor. All right. Well, you can go and get a data sheet. You find something like this. Here's my little model of 3 little capacitors. All right. So I've got a base to collector capacitance, a base to emitter capacitance, and a collector to emitter capacitance. You won't find these terms, CBC, CBE, on a data sheet. You will find something else. You'll find something called CIBO and COBO. Those are the typical names. I for input. The B is for the base configuration in which it's measured. These are not exactly the same. That's why I'm using an approximate here. So CBE is not exactly the same as CIBO, but for our purposes, it will be close enough. The collector to emitter capacitance is usually small enough that you can ignore it. So for our purposes, we're just going to say, hey, that's 0. All right, so to get these two, we'll simply look up CIBO and COBO on a graph. There is another item called base spreading resistance, R prime B, and that can have an impact. That actually appears out here on the base. We are going to ignore this. This is a fairly small resistance compared to the other circuit resistances, but it can have an impact. Okay? All right. Now, you don't just look on the data sheet and grab what it says for CIBO and COBO. Why? Because those are zero bias max values. Instead, you want to get a graph. Okay? So if you get out the data sheet, all right, so I have a data sheet from on Semiconductor that makes this 2N3904. Their stated values are 4 picofarads and 8 picofarads for COBO and CIBO. But like I said, these are max values. If you want to do maybe a low bias worst case analysis, you might use them. But otherwise, use the graph. What you need to know is what the bias voltage is. And we already determined that the collector emitter voltage was 6 volts. You can see there's actually quite a bit of variation here. This is a log-log axis. So, things as you move off from the origin, things get more and more compressed. So what I'm going to do is I'm going to find 6 volts, right? So here's 1, 2, 3, 4, 5, 6 volts. And as I go up, hit COBO, that works out to be about 1.9 picofarads. And if I continue a little further up to see IBO, that's about 2.7 picofarads. All right, so we're going to use those as our CBE and CBC values. In other words, we're going to say that CBE is 2.7 picofarads and CBC, the base to collector, is 1.9 picofarads. If we were to change the bias, those capacitances will change, and they will have an impact, of course, on the frequency response of our system. Okay? All righty. So where do we go from here? Those little capacitors exist here and here. Notice this capacitor over here is in the Miller position. So this is going to affect both the input circuit and the output circuit once we do the Miller equivalent of that. All right. So what we're going to do is a high frequency simplified circuit, AC simplified circuit. And when we do that, right, these caps will short out, these coupling and bypass caps will short out, and the power supplies will as well. And then we can just sort of redraw things the way we would, you know, in the mid-band to find gain, or at the low frequency end to find the lead networks. But we're going to wind up with a lag network on the input and a lag network on the output. And that's going to look something like this. So we had that 50 ohm on the source. We had a base biasing resistor of 100K. The Z in base is going to work out to be about 85K. So we had a beta of about 75, 1K swamping resistor, and about 130 ohms for the R prime E. So when you multiply that out, you're going to get about 85-ish K. And then we have the C in, which I'll get to in a sec. That's all of the input capacitance, the lag capacitance. And on the output end, we have the load resistor of 100K, the collector biasing resistor of 50K, just like we would when we're calculating gain, and then an output capacitance. Right? So when we look at these two things, you know, let's start with the output one first. You know, you're just looking for that RC pair of values. You know, 1 over 2 pi RC is the critical frequency. So you just want to find the Thevenin resistance associated with the capacitance. So here, these two things are just in parallel, and you're done. Back here, you know, when you look back toward the source, you're going to wind up, to get the Thevenin equivalent, you're going to wind up putting these two in parallel with RS. Right? So I basically want to find a source, a resistor, and a capacitor. So we're going to have to Thevenize this. So these two are obviously in parallel, but then when we Thevenize, we look in, we short the source, and those two things will be in parallel with the 50 ohm. Clearly, the 50 ohm is going to dominate here, right? I mean, 50 in parallel with 100K is 50. Let's be honest about this, all right? So I can then, now that I have these things simplified, I can then calculate what the input and output critical frequencies are, all right? Well, you know, where did the C in come from? Where did the C out come from? A little bit more specifically. Well, on the output end, all you really have is the C out Miller. Okay, so our gain times the capacitance, right? That'll get us a value for these capacitors. Now, the bridging capacitor, the Miller position capacitor, was the 1.9 picofarad. So on the output end, right, we're going to multiply that basically by just about 1, because it's A plus 1 over A is the factor that we need for that. So, you know, we had a gain of about 29, so you're looking at about, you know, 30 over 29, just about 1. So that just translates out 1.9 picofarads. On the input end, remember it's gain plus 1, right? Gain magnitude plus 1. So that's going to be about 30 times that feedback cap. And then we're going to add in the base emitter. Now that's not 100% correct. Why? Because of the swamping resistor. C base emitter is here, but the Millerized capacitor actually goes from here to ground. So adding them together is not 100% accurate, but in all honesty, the Miller capacitor is generally a lot larger, and just sort of tossing in the base emitter capacitor, that'll put us really close. Okay, close enough for our purposes. Like I said, don't forget there's little capacitance associated with all of these resistors, with the wiring, circuit board traces. So, we're not expecting results that are, 1% or better in terms of agreement, right? This will definitely put us in the ballpark, though. Okay, so now let's sort of turn our attention to the simulation result that we get, okay? I do have some calculations I'm going to pull up here so that we can see them, just sort of remind ourselves of what's going on, okay, with our gain and so forth. Okay, let's pull this up a little bit higher. All right, so as I said, we pulled off of the data sheet 2.7 picofarads for base emitter, 1.9 for the base collector. The C in Miller, we just took the gain, the 28.5 plus 1 times the 1.9, got 56 pico for that. Added in the CBE, there's the 59, and then the C out was just the C out Miller. All right, so basically 29.5 over 28.5, 1.9. Now, when we simplify, right, the RC over here, 50K is in parallel with the 100K, so that gets us 33.33K up to infinity. And then we take that with the 1.9 picofarads, and we get 2.51 megahertz using our critical frequency calculation. On the input end, right, we take the 59 picofarads and the 50 ohm, because, like I said, 50 in parallel with that other stuff is just going to be 50. That's going to give us 54 megahertz. All right. Okay. So let us go back and do a AC analysis on here. See where we wind up. Okay, so I have a gain over here in the midband of about 29.1, let's call it. All right, just about 29.1 dB. So I want to see where that is going to fall by 3, right? 3 dB is the half power point. So that's going to be 26.1. And I'm just going to move around here until I find 26.1. We're darn close to it. How close is that? All right, right about there. So I'm getting 2.35 megahertz for that. Okay. All right, we calculated 2.51 megahertz for the output network. Is there maybe some interaction between the output and the input networks? Now, there might be. So a little trick that we can do is to translate the other frequency further away and see if there's any impact. So an easy way to do that over here, because RS is really the determining factor, is we're just going to drop that down to 5 ohms. And I'm going to redo this. And if there's any interaction, the new frequency that we'll come up with will probably be a little higher, okay? Because what's going to happen is, each one of these networks is producing a roll-off. Well, even if this thing is at 54 megahertz, let's say, there's going to be a little bit of loss down at a couple of megahertz. That might be enough to move this just a little bit, right? So let's see what we get. All right, so there's our 29.1. Again, we're looking for 26.1. Oops, a little too far. Right about there. Oops. Come on. All right, well, that's about 2.44 megahertz. So that's a little bit higher. It's a little bit closer to our calculated value too, right? So there apparently was a little bit of interaction. All right, a little bit of interaction there. Okay. Now that brings up an interesting question, which is, how do I now find the input network? So we've pretty much determined the output network. All right. The system, in other words, the combination of the two, produces an F2, an upper break frequency, all right, from the simulator at 2.36 megahertz, right here. And we notice that most of that is from the output network, which is supposed to be coming in from our calculation at 2.5 megahertz. But there's apparently a little bit coming from the input network too. That's why we get something that's just a little bit off, right? It's a little bit low. So that when we put in the 5 ohm, that pushes it up higher. There's less interaction, and this comes up a little closer. We get 2.43. But how do I determine this exactly, or at least, you know, with some degree of accuracy? Because it's a lot higher than this one. Is it easy to translate this one up so I can just look at this one? Well, the answer is no, unfortunately. However, what we can do is sort of go the opposite way with this. So instead of using the original 50 ohm, I am going to crank this up to 50 k ohms. So we're going to push this one down. All right. In other words, I want this one to come out to be a lot lower than the natural critical frequency on the output. In other words, that 2.5 megahertz. If I can get this way down, if I can get this down at, you know, 100 kilohertz, 50 kilohertz, something like that, the impact of this output network at 2.5 meg will be minimal. All right. So I need to recalculate this. I need to recalculate what the input is. I can't just say, oh, it's 1,000 times off because I went from 50 ohms to 50 k ohms, because now we can no longer just ignore our B and Z and base. We have to include those. Then I can redo my computation. But before we do that, let us see what we get. All right, so our gain has actually dropped down a little bit, right? We're at 23.5 dB. And the reason is because we're losing a lot of input signal on the 50K. You know, when it was 50 ohms compared to the ZN, it was no loss at all. But now that there's 50K out here, we're going to actually lose a bit of signal. But the important thing is, what is the midband gain? So that's 23.5. So I need to find 20.5. Yeah, right around, where are we? Right about there. Okay, so it's kind of like in between 99-ish. Come on. Yeah, so yeah, we're actually in between. So we'll just call it 99, I think would be good enough. All right, so our translated frequency is 99 kilohertz. Well, how much of a shift was there when we put in the 50K? Well, we can calculate that. All right, so the new value for the input resistance for the critical frequency here is going to be the 50K in parallel with the 100K in parallel with the Z in base, which we said was 84.8K, something like that. Anyway, that whole thing works out to 23.9K. So compared to the original 50 ohm, we've increased the total resistance by a factor of 480. So our effective critical frequency should be 480 times higher than this, right? Than the measured 99 kilohertz that we have. So you multiply those out and you get 47.5 megahertz. That compares against the calculated 54 megahertz. So the output network actually matched up really well because our calculation was 2.51 megahertz. And when we translated the input network out further, we got 2.43 megahertz, right? You can, in fact, actually calculate what the true loss is at a specific frequency, like 2.36 megahertz in the original circuit. But that's not something I'm going to chase down here in this video. Suffice to say that the output network is coming in quite accurately. The input network is pretty good, 47.5 meg versus 54 meg. Not quite as nice. Possible reasons for that? Well, that R prime B that I mentioned. That is one possible thing that would add some resistance in and shift this down, because I would have a little bit more than 50 ohms, and that would push this down closer to what the simulator is giving us, right, the 47.5. Okay, So far, so good. I did mention at the beginning that the bias does play a role here. So let me bring this input resistor back to its original value. And in this circuit, right, just to recap, with the original value, the simulator gave us a break frequency of 2.36 megahertz. All right. If we change the bias, and I'm going to do this real simple like by just cranking up this power supply here to 25 volts. Okay. Now the current is set up down here. Really, this VCC will just set up what we have for the collector to emitter voltage. So this is going to jump from 6 volts, since we've added 10 volts to this. This is going to go from 6 to about 16. And if we look at the graph, oops, wrong button, sorry about that. And if we look at the graph, right, as we go up in that voltage, we get less capacitance. So with less capacitance, we should get higher critical frequencies, right? If this is all correct, then we should see something higher than 2.36 megahertz, right? I'm not going to go through the precise computation, but just to sort of prove a point, all right? Okay, let's get our cursor out here. And we're back to 29.1-ish. So I need 26.1, 26.14. Okay, we're getting 3.12 meg. 3.12 megahertz. 3.12 megahertz. Versus 2.36. Right? So that cap definitely made an impact. And in fact, it's going to change both the input and the output networks. You know, how much each is changing, I'm not sure. We could grind through the calculations with new values for the CIBO and the COBO. But the important thing is we can see that the bias does have an impact. Let's bring this guy back because I want to show you one more thing. And that is we can exploit Miller's theorem. We can use it to our advantage. Many times amplifiers have a bandwidth that's too wide. You know, if this was an audio amplifier, we don't need to go up to a couple of megahertz. There's good arguments to not do that. You know, up there's radio frequency traffic. I don't want my audio amplifier to pick up those signals. That could cause interference. So I want to limit it maybe to something closer to what the human frequency range is. You can hear up to about 20 kilohertz. You know, young, healthy people with good hearing, you can hear up to about 20 kilohertz. So, you know, we can artificially reduce this upper break, the F2, by adding some capacitance. Now, you could just sort of brute force this and add some lag capacitance here and here, but it's more effective if we just take a capacitor and put it in the Miller position, because now it's going to affect both the input and output networks. This sort of doubles up on whatever your CBC is. All right, so I am going to change this. I'm going to use a factor of like 10. So let's make this 20 picofarads. Not exactly 10, but close enough. So this extra capacitance will get Millerized on the front end, and it'll also add to the output, and that should have both critical frequencies drop down considerably. So we're not going to be looking at megahertz anymore. If we wanted to, we could do the whole translation scheme to find the input and the output, but just as I did a second ago, I just want to make sure that the F2 for the system has been brought down. We can chase the details if we want to. That might be a nice exercise, but for now, let's just verify that it does in fact happen. So, okay, 29.1 dB, so we need 26.1. Right about there. And you can see we are down to 211 kilohertz, right? All right, just by adding that one little 20 picofarad cap. That's all it took, one little 20 picofarad cap. Okay, so to recap, when we look at the high frequency response, it is primarily these little capacitance values, parasitic capacitance that exist around the transistor. There, in the real world, there are also some small capacitances associated with your resistors and wiring and so forth. So we come up with a couple of lag networks, one on the input, one on the output. It's sort of the mirror image of the lead network response. It's the lower of the two that's going to dominate the response. You can very easily, by adding a capacitor in the Miller position, decrease the frequency response, decrease the F2, limit the bandwidth. And before we go, I'll just say there is no easy way, underline easy way, of extending the bandwidth. You can drop the F1, the lead network response, just by making bigger capacitors here. You can't do that sort of thing on the high end. You're sort of stuck. You either find a transistor that has lower values of CIBO and COBO, or you redesign the circuit. You change the resistor values and the bias and so forth so that you can get a higher critical frequency. So it's a much more involved process trying to extend the high frequency. Reducing it, easy. Extending it, not so easy. Doable, but not so easy. Okay, well, we covered a bit in this video. I hope you enjoyed it. We'll see you next time.